morning, everyone. Today we have Professor John Schuller from University of California, Santa Barbara. He is an assistant professor there in Electrical and Computer Engineering department. He received his PhD from Stanford and was a fellow in Columbia University Energy Frontier Research Center. And his research interest is focused on nanophotonics, plasmonics, metamaterial, and CMOS-compatible photonics. He is the recipient of Air Force Office of Scientific Research Young Investigator Award and very recently NSF Career. So let's welcome John.
Well, thank you to ARCA for the introduction and the invitation to come speak here. This is my first time at Seattle. So I have been an assistant professor at Santa Barbara for 2.5 years. And so much of what I'll be talking about today are actually unpublished results on projects that we've only very recently started. So for the purposes of bad alliteration, I've divided my talk into 4 M's. So we'll start with a motivation where I'll talk to you about this term optical antennas. So today I'll be talking about semiconductor and molecular optical antennas, and specifically focusing on the idea of measuring and manipulating the radiation patterns. Okay? So I'll start by telling you what I mean when I use this term or this analogy of optical antennas, and specifically why we care about the radiation patterns. We'll talk about modifying radiation patterns or trying to make reconfigurable phased array optical antennas. And then I'll go on to the idea of maximizing the response of what we're looking at by engineering the types of light beams that we use. And lastly, measuring. The idea here is looking at molecular materials and by measuring antenna-like effects in these materials, trying to understand something new about their optical properties. Okay. So let's start with the first thing, motivation. And what I have up here on the screen is just a very simple schematic of how you might imagine a conventional radio frequency antenna that you might find in your cell phone or radio works. We have an illuminating plane wave over here, illuminating radiation, interacting with this kind of canonical split dipole metallic antenna, right? So the electric field from our light causes the electrons in the metal to oscillate, and those oscillations become resonant when the size of the structure is roughly half the wavelength of light. And of course, the reason why we want to set these electrons and currents resonating is so that we can force the currents to drive through some load, which at radio frequencies can be much smaller than the wavelength of light. Okay. So the idea is this antenna structure mediates power transfer from light or electromagnetic radiation in free space to a load which can be much smaller than the wavelength. Okay. So in recent years, people have taken this concept to optical frequencies, and there's really 2 main new science ideas that are involved in doing that. The first is that our metals at optical frequencies no longer look like perfect conductors, so we have to think about the different optical properties of metals at visible and IR frequencies. And of course, the types of loads that we want to couple the radiation to can be very different, right? So we don't have optical frequency circuit loads. We might be trying to interface our radiation with some kind of sub-wavelength, let's say, molecule, or if we look at these various applications, these are all examples of using an antenna or an optical antenna-like structure to interface or efficiently couple electromagnetic radiation to, let's say, an ultra-small photodetector for doing high-resolution microscopy, single molecule sensing, or just to enhance light-matter interactions. Okay. So these are all types of applications I discuss in the review paper up there. And what I'll be talking about today is not so much the applications or the idea of interfacing with these nanoscale loads, but, so before I go into that, so just as you can open an antenna textbook like Balanis and see that there are many different designs of antennas, in the last 10, 15 years, people have really been able to make optical frequency analogs of all those. Okay. So as I was mentioning, rather than looking at the applications or the types of nanoscale loads that we'll be looking at. In this talk, I want to focus on two aspects, which are that these various different optical antennas have, of course, various resonant spectra in terms of the energy at which they efficiently couple the radiation. And then mostly I'll be focusing on here the idea that they can scatter or emit light with very directional or distinct radiation patterns. Okay? So because we're interested in this idea of engineering or measuring radiation patterns, what we'll be thinking about today is looking at a spherical antenna, right? So if you're interested in radiation patterns, a spherical structure is the ideal basis set for building an arbitrary sort of radiation pattern in three-dimensional space. Okay. So if you want to understand how some spherical structure interacts with light, the way you do this, or the way one would do this, is you take the vector wave equation, which describes how light propagates, decompose it into spherical harmonics, and match some boundary conditions at the surface. Now, if you're interested in doing this, you're in luck because this has already been done by me. And, oh, excuse me, there's a typo there. It was not done by me, but by me. Okay? So what Gustav Mie did is he figured out these decompositions and established this theory. And so what I'll show you now is the response of the system that we'll primarily be talking about, which is a spherical semiconductor structure. Okay? And what I'm showing on the board here, the graph there, is a plot of a scattering cross-section. Let me find my cursor. Here we go. So we have a scattering cross-section as a function of a normalized frequency variable. Okay, so this is the ratio of the radius of the spherical particle divided by the wavelength. So what we would typically measure is this black curve. This is the total scattering from our structure. And what you can see that I've drawn here is this total scattering comes from a superposition of different multipole orders. Okay? We have the lowest order mode is this magnetic dipole resonance here, the solid blue line. We have an electric dipole resonance as the solid red, and these dashed lines are quadrupole resonances. Okay? So what do we mean by these multipole resonances? Well, if you were thinking about this microscopically in electrostatics, we would associate our electric dipole mode with two charges, a plus and minus charge, and the fields associated with that. So to go from a dipole to a quadrupole, we have four charges with an antisymmetric arrangement. And our microscopic model of a magnetic dipole is that we have some circulating currents which produce strong magnetic fields. Okay. So for the purposes of this talk, what is really important is the idea that each one of these multipole resonances has a distinct field distribution or radiation pattern. Okay? So to summarize in terms of the introduction, what my group is interested in doing is both understanding and engineering these radiation patterns of semiconductor and molecular nanostructures. Okay. So let's move on to the first subject area, which is the idea of modifying the radiation pattern. So how can we engineer these semiconductor nanostructures to generate a desired radiation pattern of interest? Okay. So the analogy here we're taking is we're looking at optical frequency analogs of phased array antennas. Okay? So phased array radar or phased array antennas is a very important and mature technology. We can take an array of different of antennas, and by controlling the phase relationship between them, if we're thinking about emission, we can steer the radiation lobe of our antennas, or if we're thinking about these as receivers, we can be sensitive to radio frequency light coming in from a certain direction. Okay. Now, these optical frequency analogs have actually been made in the last 5 years or so, and we often in my community call them metasurfaces, but really they are optical frequency analogs of phased array antennas. Okay. So the way this works is you take a single metallic antenna-like structure, and by controlling its size and shape, we can go down here and control the phase of light that is scattered off of it. And so by controlling the phase relationship in space, one can, for instance, make a diffraction lobe or focus beams according to these phased array principles. Now, what I've shown you here on the screen are examples of static phased arrays. This is all based on engineering the size and shape of these antennas. And once you've done that, you're stuck with your design. It does the one thing that you've designed. So what I'm going to be talking about today is trying to do this in a reconfigurable or tunable fashion. Okay? So the student who's leading this work is Prasad Iyer. He's getting married in 2 weeks, so he's been very productive trying to get a lot of this work out the door so he can enjoy his wedding and honeymoon. Okay? And so what we'll look at is we're going to zoom in on one of these scattering spectra I showed you. And now what I'm showing you is just the magnetic dipole mode of one of these spherical structures. Okay? The red curve is the amplitude of the response. So we have a resonant amplitude response. And like any resonator, as we have a resonance in our amplitude, we have a pi phase shift, or a shift in the phase. Okay? So how can we use this coupling between amplitude and phase to make a directional antenna? Let's start with sort of a very basic few element antenna, something like a Yagi-Uda antenna design. Everything I'm showing you here has multiple elements, but the basic way this works can be understood just by looking at two of the elements in these pictures, just by looking at the relationship between the reflector and the feed. Okay? So if we have let's start with two identical spherical particles. What we know is that if we shine light on it, so in my group we're very interested in infrared radiation, so we're going to be looking at light with a wavelength around 10.6 microns. So if I shine light, by symmetry, these spheres must scatter as much to the left as to the right. Okay? So we would have a symmetric scattering lobe. And I put this black dot on the screen to show the idea that maybe we design their sizes to be at peak resonance. So how would we make a diffraction lobe? Well, we need to break symmetry. So the idea here is we can have two different size particles. One is larger than the other. So now we have two black dots. They are equal in amplitude, but one is detuned to lower frequency and one to higher frequency. So they have equal amplitude, but if we look at the intersection with the phase curve, they have a pi/2 difference in phase. Okay? So this pi/2 difference in phase, when coupled with the spacing that gives us a pi/2 propagation phase, can either add up destructively, pi/2 plus pi/2 is pi, so that's a destructive interference, or constructively. If I have pi/2 minus pi/2, that's 0, they're in phase. So we would get out of a system like this is a directional radiation lobe pointing to the right. Okay, now as I mentioned, what we're interested in doing is doing this in a reconfigurable fashion. So rather than changing the size, the idea we want to look at is whether we can mimic the effect of changing the size by changing the refractive index. Okay? So what I'll be looking at is how the response of these antennas changes as we introduce free carriers into the semiconductor. Okay? So this could be done electrically or as shown up here optically. For now, let's not worry too much about how we get the carriers in. We're just going to do some calculations where we imagine what happens as we introduce free carriers. Okay, so again, the idea now is it's reconfigurable because if we introduce them to the left, we get a diffraction lobe to the left instead of to the right. Okay, so this is a plot of indium antimonide. We're interested in indium antimonide because it has a very low effective mass. Okay, so I'm showing you again, in red is the amplitude of the response, in blue is the phase. Okay, now I'm going to show you an animation where we look at how this curve evolves as we increase the free carrier density inside our semiconductor. Oops, let's go back. So what I want you to look at when you see here is that everything shifts to the right, okay? So we're reducing the refractive index of the material, which is analogous to, in a sense, making it smaller. So our resonances shift to higher frequency or shorter wavelength, okay? And I also want you to notice the amplitude of this peak in the red, which stays relatively constant. So even though we're introducing free carriers, actually the dissipative effects are minimal, and the amplitude of the response stays roughly the same. And I'll talk about that, this particular value that we're seeing and what it means. Okay? So how might we use this type of effect? Again, we'll go to our simple 2-antenna system. If we start with, let's say, on the order of 10 to the 17 free carriers, we get a symmetric lobe. And then now, as we introduce free carriers into one of them, we get this directional lobe that appears. Okay? So the idea, again, is we're going to use interference between two particles to create a diffractional lobe. Okay? And this optimal directivity happens when we have about 10 to the 18 carriers per centimeter cubed. Okay. Now, one of the unique things, as I mentioned about these antennas, is that we have not only this magnetic dipole resonance, but we also have a higher order mode or an electric dipole resonance. Okay, at higher frequency is what I mean when I say higher order mode. So the solid lines are the response of our magnetic dipole. Again, red is amplitude, blue is phase. Dashed lines are the electric dipole response. Same thing, red is amplitude, blue is phase. Okay? So now what I want to show you is that because of this unique property where we have these different multipole resonances, we can create directional radiation patterns not just by interfering two different particles, but within a single particle by controlling the relationship between these two different modes. Okay? So again, the black dot here is a starting design principle. Okay? So we can imagine an unpumped sphere where we design our wavelength to sit right here. So the amplitude of our two modes is equal, but the phase, if we compare the blue curve of our electric dipole mode to the blue curve of magnetic dipole, the phase is at a maximum difference here. Okay? So when we design our particle in this way, what we see is that we primarily get a reflection lobe. So what I'm showing here, for purposes, it doesn't really matter why exactly, but when the lobe points down, that means that we primarily get reflection. Okay? So now as we introduce free carriers, all of these curves are going to shift to the right. And so what we're going to look at is if you keep your eye focused on the dot, it's sitting here at about 0.15. And so now if we introduce free carriers for that same wavelength, our amplitude and our phases are equal. Okay? So what happens is we pass from one side of resonance to the other. I'll show you now again in this animation. And what you'll see is our reflection lobe primarily becomes a transmission lobe. Okay? So by controlling within a single particle the relationship between these two different modes, we can also create directional radiation patterns. Okay? So how might we use this in a phased array? Well, here now I'm going to go from these single particles to looking at arrays of these spheres. We can see this is a plot of transmission as a function of the radius of the sphere and the periodicity of the array. And what you'll notice is that if we're detuned from the electric and magnetic dipole resonances, right? So this was that spot I said where we can have the amplitudes and phases of the two modes are equal. And so this white line that I'm showing is a trace where we show that if you change the periodicity, we can have unity transmission, but our phase goes through a 2-pi phase shift. Okay? So this is the basic kind of idea that we're going to use, but for making a phased array, you don't really want to control periodicity. Again, what I said is what we do is by introducing free carriers is effectively like changing the size, okay? Or like this black line cut over here. So instead of looking at spherical particles, what we want to do is design a resonator where both the magnetic and electric dipole modes are at their peak resonance at the same time. So instead, I'm going to talk about disk arrays, right, or these top-down fabricated truncated cylinder structures. And now we have an extra degree of freedom. We can look at how the transmission resonances change as a function of both radius and height, or really the relevant factor here is the aspect ratio. Okay? So we should see here is that there is a dip in transmission from the magnetic dipole mode, and similarly one from the electric dipole mode. But when they intersect in the center, because of their relative interference, you actually get our minimum reflection and transmission become unity transmission. Okay? So what Prasad did was looked near this region. So if you use the right aspect ratio disk, what you see is that now I'm plotting transmission as a function of periodicity and wavelength. And what you see is that there's a large region of parameter space where the transmission is unity. Okay, so now we can operate near this region and look at what happens as we introduce free carriers. And the key result here is our blue curve, which is that the phase evolves over 2 pi. Okay, so by introducing free carriers on the order of up to 10 to the 18 per centimeter cubed, we can get a 2 pi phase shift in our array. The transmission is not strictly unity everywhere, but we have less than about 2 dB of change in transmission. Okay, so it's not perfect, but it's a good start because no one in the community has really figured out how to get these 2 pi phase shifts in a reconfigurable fashion. Okay, so how might this look? So these are just calculations. We're now working on experiments. So how might these ideas be translated? Well, the idea here is we have some array of resonators. And instead of looking at what happens when we change the carrier concentration in all of them, we need some way to change the carrier concentration in space. Okay? So one idea, just schematically, might be we use a pump laser, like a visible pump laser that's connected to a spatial light modulator, so that an intensity profile in the visible, right? So if we have different intensities across our array, we get different absorption, different generation of free carriers, and so our intensity profile in the visible becomes a phase profile in the IR. Okay? So that's one way you could imagine implementing it. Right now, we're actually focused not on these zero-dimensional or spherical-like resonators, but on 1D resonators. Okay? So here we have something like an indium antimonide rod. Again, it has a non-square cross-section, which allows us to engineer simultaneously an electric dipole and magnetic dipole-like mode that overlap in frequency or wavelength space. And these are calculations, again, but Prasad is now working on building this. So the idea here is to use a PN junction in this indium antimonide or indium arsenide system. And on the right of the screen, what you see are calculations that have full device-level modeling of the carrier concentration within this structure. And as you change the voltage across it, we combine our device simulations with electromagnetic simulations and show that you, at least in our theory, can get a highly directional radiation lobe that we can now steer by changing the voltage gradients or voltage profile across our array of resonators. Okay? So Prasad's working on implementing this experimentally. In the meantime, my postdoc, Tomer Louis, was looking at demonstrating these kinds of effects in actual silicon and germanium spheres that he fabricates with a bottom-up femtosecond laser machining approach. Okay? So the idea is we take a highly focused femtosecond laser, shine it on the surface of a semiconductor, and it hits the semiconductor, material ablates and cools as it comes off, and comes back to the surface. And so we decorate the surface with spheres, and we can move around and change the conditions, change the intensity or power of the laser. And in doing so, we can create very nicely spherical semiconductor particles with sizes in this micron regime and with optical resonances that really span the infrared. Okay? So we can look at sub-bandgap wavelengths where these materials are effectively lossless, and we can look at things like this. So what I'm showing up here is a scattering spectrum, an experimental scattering spectrum of a single particle in red. And we're comparing it to our me calculations in black. Okay? So firstly, I just want to say that these kind of measurements are not trivial. We're the first group we know of that have looked at infrared spectra of particles this small. And what you can see is that we have these multipole resonances. Here's a magnetic dipole mode in the associated theory. We can explain these shifts due to substrate effects. Here's our electric dipole modes. We can see the quadrupole. And then over here, you might think it's not so clear that these little features in our experimental spectra correlate to our calculations. So one of the nice things by having all these different sizes is that Tomer can look at how these resonances evolve in wavelength as he looks at particles of different sizes. Okay? So these are different sizes. This is the resonance wavelength. And these are the first 6 multipole orders. Okay? And the solid lines are parameter-free lines that we get from Mie theory. And we can see that, indeed, we can observe these resonances spanning the IR from 2 to 15 microns, and that we can reliably catch even up to our hexapole order. Okay? So we can identify these Mie resonances even to these very high orders that haven't really been reliably seen before. Okay? But what I really want to show you is how we can tune them, or the idea of tuning them, with free carriers. Okay? So we can look at, as we change the doping level in these spheres by starting with different doping density semiconductors. And we'll start with the silicon. And the case here is that if you look, there's really a huge difference in the evolution of this magnetic dipole resonant wavelength with size from an undoped sphere to a heavily doped sphere over here. Okay? So while we don't, in this measurement, yet have access to the phase of the response, we can certainly see that we can get very large tuning of the resonance frequency or wavelength with free carriers. And we can also see that in the case of germanium, we get a larger response because of the lower effective mass. Okay. And so actually, if you look at this difference between our undoped and heavily doped particles, we can actually access a plasmonic regime where we have enough free carriers that our silicon does not behave like a dielectric anymore, but behaves like a metal. Okay? So what I'm showing in this plot here is the location of an electric dipole resonance as a function of size. And we have a electric dipole mode when the refractive index is positive, when the particle is undoped, so we see large field intensity inside the sphere. And at high doping levels on the order of 10 to the 20, we see a similar electric dipole mode. The radiation patterns are the same, but now the material has a negative epsilon, or permittivity. It behaves like a metal. There's no field internally. Okay? And the signature that we see to identify that this is indeed a plasmonic mode is by looking at very small sizes. We see that the electric dipole resonance wavelength plateaus. Okay? And this is a signature of what's called an electrostatic resonance, which is it's a size-independent or scale-independent resonance. And here we know that at this wavelength and this doping level, the dielectric function of silicon is around -2. Okay? So to summarize this part of the talk, the idea here is my group is pushing towards using these free carrier refraction effects in semiconductors to make reconfigurable infrared optics. Okay? Things like optical antennas and metamaterials. So now let's transition to the next part of the talk, the idea of maximizing, right? So we have one of these spherical antenna-like structures, and now we want to think about how can we maximize the light-matter coupling, okay? So now what I'm plotting here is a scattering or extinction spectrum of one of these magnetic dipole modes, again as a function of this normalized frequency. And I've plotted it in these funny units. Okay, we've plotted the cross-section, which has units of area, in terms of lambda squared over 2 pi. Okay, so why do we do that? Well, it turns out, I've shown in the past, that there is a fundamental limit to this dipolar scattering cross-section. It cannot possibly be larger than 3 lambda squared over 2 pi. Okay. Now again, it's important to understand this is just for a single mode. Okay. And we can also show that if we have a semiconductor or dielectric resonator with no losses, it necessarily has to reach this fundamental limit. Okay. Which is to say that our antenna cannot be any better. It is as good as you're going to get. There's nothing you can do to this material or changing its size and shape that'll give it a better multipole response. Okay? Now this might seem odd at first, especially because when we look at what we've drawn here, nowhere in this limit does it appear the size of the structure. Okay? So this limit equally well applies to a micron scale antenna structure like we're seeing here, and to something that's 3 orders of magnitude smaller, like an atom. So how can these things have the same limit on their dipolar scattering or extinction spectra? Well, I know there's some math on the board, and probably I lost a couple of you already just by putting equations, but it's really very simple, okay? So up here we have a description of the incident plane wave. So we have plane wave illumination as a superposition of different multipoles. And down here I'm writing out the scattered fields. Again, it's a superposition. And now this limit corresponds to this coefficient here, let's say, equaling 1, which is to say that we have as much power or intensity in a given multipole order in the scattered wave as the incident wave. Okay. So what am I saying? What I'm saying is that this limit means that our plane wave has a finite amount of its power, a finite percentage of its power in, let's say, the magnetic dipole mode. Okay? So regardless of the size of the structure, we can only take that and radiate it outwards. Okay? The orthogonality of the modes means we can't convert one to the other. So if we want to maximize the interaction of our beam with the particle, what we need to do is change the parameters of our incident beam. We need to engineer the beam to match the radiation pattern of the mode that we're trying to couple to. Okay? So this is the idea we want to look at, is to maximize the coupling to these multipole excitations, not by engineering the antenna, but by engineering the light source that we use to interrogate it. Okay? So this is a project of my grad student, Tanya Das. And what the first thing we needed to do to understand how real, not plane waves now, but focused real beams interact with these particles, we needed to develop the theory to do that. Okay? So there's really 2 primarily different ways to do this. The first is to take your finite beam and decompose it into a spectrum of plane waves. Okay? So for each plane wave, I can determine its me response, and then I add them all up, and I have matrices to account for the different angles of incidence, and I add up their response. Or you could take your incident field, and the decomposition's a little harder, but you can decompose it into spherical waves and get the response directly. Now, in both those cases, you have to know the field everywhere on a surface. You either, in the Cartesian case, have to know the fields everywhere on a planar surface to do your decomposition, or on a spherical surface to do the spherical decomposition. But as we were working on this problem, what occurred to us was that by thinking about how this relates to a multipolar Hamiltonian, we should actually be able to develop a local field approach, where you don't need to know the fields everywhere on a surface, but only need to know the fields at the location of where this particle sits, or where this antenna sits. Okay? So in the multipolar interaction Hamiltonian, each multipole interaction is described by something that is intrinsic to the material, something like a magnetic dipole moment, and something that depends on the nature of the light source. So the magnetic dipole is driven by a magnetic field. Electric dipoles by electric fields. Electric quadrupoles here are driven by a field gradient. So the Q here would be something intrinsic to the material, and the del dot E is the gradient that drives the quadrupole response. Okay? So I won't go into the proof. It took us some time to be able to prove that actually we can recast me theory, not in terms of these decompositions, but entirely based on a local approach. So the idea here, again, is that all of our multipole resonances have something that depends on the material, like a me coefficient, and something that depends on the nature of the light source, like the magnetic field intensity or some kind of a field gradient. Okay? So we have an analytical proof to show that you can recast me theory in this way. Here we show that whether we do this in terms of a plane wave decomposition or local field, we get the same results for interaction of a focus beam with the particle. So now, based on these intuitions, so this local field method, I think, really helped us both in terms of the computational complexity, but also in terms of the intuition of what happens if we look at not a linearly polarized wave, where we have all of the multipole orders, but something like an azimuthally polarized wave. Okay? So we can design a light source, for instance, an azimuthally polarized light source that has no electric field at its origin, no electric field gradients, and we only get our magnetic modes. Okay? So then, according to our calculations, we'd see something like this. We would see only our magnetic modes in the scattering. Or we could look at radially polarized, and we have electric dipole modes, and then we would see the green curve. Okay? So the idea here is we can take the same object, the same antenna, which we think of as having this characteristic spectra, and we can actually very drastically change the nature of the scattering spectra, not by changing anything about the particle, but by changing the nature of the light source that we illuminated. Okay? So if we had a white light source with these different polarizations, the color of the particle would appear to be very different depending on the nature of our light source that we use to study it. Now, it's not just the spectra that change, right? So here we see that we have certain modes appear or don't. It actually turns out, and this comes from our local field theory, that the radiation patterns, even though the spectra occur at the same position, are also very different. So why is this? Well, we can start with the dipole mode. This is a little bit trivial. If I have a linearly polarized wave, we would get an in-plane field, okay? And so we would see a characteristic donut mode. And if I had a radially polarized light source instead, I just get a reorientation of the field. So now instead of pointing along X or Y, it points along Z. So we're focusing down like this, and at the focus we have a Z-oriented field. Okay? So that's sort of a trivial rotation of the radiation pattern. It turns out to be a bit more complicated when we look at the quadrupole modes. So the canonical picture of a quadrupole mode is a transverse quadrupole. I take a dipole, and I interact it with an oppositely oriented dipole, right? So that's something that's driven not by fields, but by the gradient, the transverse gradient, or the derivative of Ex along Z. Now, in contrast, in our radially polarized source, what we see are longitudinal quadrupoles. Okay? So this was a surprise to me. It's not something I was expecting to see. By changing our light source, we can actually access totally different modes or totally different resonances in the particle. So now what we're looking at is, instead of a quadrupole where we have them transversely oriented, they're longitudinally oriented. And so it's driven by gradients such as dEz by dZ. And if you look here at the radiation pattern, it's completely different. The symmetry of this is completely different. Okay. So these, if you think about the plasmonic or metal antenna analogs, this type of excitation was long thought to be dark or non-existent. Okay. So our realization was, well, maybe when you put two metallic antennas in this arrangement, you don't ever see this longitudinal quadrupole, not because it's not supported by the particles, but because we're using the wrong light source to look for it. Okay? So the idea here, again, is by engineering our light beams, we can affect the type of modes that we see, the amplitude of that, and even look for new types of modes. Okay? And so lastly, the idea I had alluded to, one of them was a selective excitation. If we come in from both sides, we can mimic one of these multipole field distributions and try to excite just a single mode. Okay? So this would now give us sort of selective coupling to a desired multipole order. And that's something you could use to look for these multipole effects, not in materials that we can easily simulate on a computer, but in things like heavy atom phosphors, which Chris Dodson in the audience knows quite a bit about, or in quantum dots, where it's recently been discovered that the luminescence or light emission from these materials has multipole effects or multipole resonances in it. Okay? So if you wanted to do the same thing, but looking at absorption instead of luminescence, rather than measuring the output, we would control the input. Okay? So that's the basic idea, something we might be able to use from these ideas, where we're very actively now looking at how we can use beam engineering to enhance, to have selective and enhanced coupling to multipolar interactions. Okay. So the previous section, I finished off with the idea of how what we study in these semiconductor antenna systems can inform our understanding of optical processes now in molecular materials. Okay? So that's the last part of what I'll talk about here in the talk, is looking for these antenna-like effects in molecular materials. Okay? So this is work that began when I was a postdoc and I finished up at Santa Barbara. So I was a postdoc in an energy center, and there I became very interested in organic photovoltaics. And what was unique to me about these organic semiconductors that are used in organic photovoltaics is the existence of these highly ordered morphologies, right? So in the semiconductors I've been talking about, the individual atomic constituent has some spherical symmetry, and then they arrange into a highly ordered and isotropic crystal. And in organic, we might have, let's say, a polymer, which looks like a one-dimensional strand of spaghetti, or a planar molecule, right? So we start with a constituent that's very anisotropic, and it turns out that these things naturally, without really any effort, tend to self-assemble into highly ordered structures. Okay? So it's shown here. So now if you look at the optical properties of these materials, so if you call someone up at NIST, right? So if he doesn't know what the optical anisotropies are, no one does. So if you ask Lee Richter, what are the anisotropies in this material? He'll email you a curve like this. So the blue curve, this is a measure of light absorption from ellipsometry. So the blue curve here is when the electric field of our light is oriented in the plane, okay? So this is a schematic of a polymer, P3HT. It's kind of the fruit fly of the organic photovoltaics world. And so the blue curve is when the E field of light is oriented in plane, the black curve when it's oriented perpendicular to the surface, okay? So these are huge optical anisotropies. This material only absorbs light when the E field is oriented in plane, not at all when it's perpendicular to the plane, okay? So these optical anisotropies are present. What I want to talk to you about is comparing two layered systems, so systems where we start with a planar constituent and stack them, okay? So we'll talk about molybdenum disulfide, where we have a weak interlayer coupling, versus an organic system where we have strong interlayer coupling. And now the idea here is that these anisotropies are going to relate to distinct excitations. So an in-plane excitation, right, we would call something like an intralayer exciton. It's happening within one of these layers. We want to see if we can compare, by looking at anisotropies, these in-plane excitons to an out-of-plane oriented dipole, something that we would consider a between-layer or interlayer exciton, something where we separate the electron and hole between layers. So that's the idea, right? So we would look at two different orientations of the dipole. Now, instead of looking at the linear properties as we do in ellipsometry, I'm going to be talking about luminescence. So the plot here we have is the relative intensity for two equivalent strength dipoles, the luminescence intensity as a function of emission angle. Okay? So these are calculations showing that the distribution of light is very different depending on the dipole orientation. So rather than thinking in terms of angle, it's actually a little bit easier when we do the math to think in terms of the photon's momentum vector projected along the plane of the substrate, k parallel, right? So this is just our angle gets translated to a momentum. And the reason we do this is you can see that we have very different behavior, in particular at the critical angle, the angle of onset of total internal reflection at the air interface, okay? So really what I'm going to be showing is mainly by looking here, we can distinguish between light coming from different dipole interactions, orientations, okay? So how do we do that? This was done in collaboration with Rashid Zia at Brown, where instead of doing conventional imaging, right, so in conventional PL imaging, every point on my CCD chip corresponds to a distinct position on the sample. So what Rashid developed was a Fourier imaging technique. Okay, it's very easy to do, where now every point on your CCD chip corresponds not to a position on the sample, but to a distinct angle of emission coming from the sample. Okay? And for these two-dimensionally symmetric layered materials, we actually don't need this two-dimensional angle information, so we can project that image onto the entrance slit of a monochromator and separate the light by angle in one direction and wavelength along the other axis of our CCD. Okay? So what do we get? When we look at, let's say, a monolayer of MOS2, at every wavelength, we get a plot of the PL intensity as a function of the emission angle. Okay? So now I'm showing you from -1 to 1, or a little bit larger range. Red is p-polarized light. Okay? P-polarized light comes from a combination of in-plane and out-of-plane dipoles. The blue is S-polarized light, which only comes from in-plane dipoles. Okay? So these are experiments, and what we did was fit our p-polarized data to determine how much of the light is coming from in-plane dipoles and how much from out-of-plane dipoles. Okay? And in doing so, we generate a parameter-free independent fit of the S-polarized data. Okay? So the key feature here is, if you remember the calculations I showed, our dip goes basically to 0 at the critical angle, which is a signature that we have only in-plane dipoles in our material. Okay? So the blue curve here is what we get from a monolayer. So we were able to demonstrate directly that in a monolayer of MOS2, we have only in-plane oriented dipoles, or we separate the excitons within a layer, not surprisingly. But as we go from monolayer in blue to bilayers in green and trilayers in red, there's an indirect gap feature here, which we thought might be related to charge transfer or interlayer excitons. We can show definitively that it's not, okay? That this indirect gap feature still corresponds to an in-plane dipole moment. So now I want to contrast that with an organic system. This is a planar molecule that, again, stacks. And now this organic molecule has much stronger interlayer interactions, okay? And so even though the absorption looks like you only have in-plane dipoles in absorption, when we look at the luminescence, it turns out that our dip no longer goes anywhere close to 0. Okay? So when we do our fits, the dashed lines again are fits, what we see are two different spectra. These are the results of fits again, and we see that we have, we can back out the extrinsic collection-dependent effects from our optics to get at something like an intrinsic dipole strength. And we can see that our out-of-plane oriented dipoles, actually, if you kind of draw a line, are sort of shifted in space. Okay? So the idea of what we think we're seeing here is that in the system we have two types of excitons, a normal intralayer excimer state with an in-plane dipole moment and a charge transfer state where we actually separate the electron and hole between two molecules. Okay? Now this comes from fits, so one might have a bit of skepticism. Turns out our life in this particular case is made easier by the fact that we have this unique behavior at the critical angle where the light from our in-plane dipoles goes to 0. So if I make a measurement over here, at normal incidence, I only see light coming from my in-plane oriented dipoles. And over here, I only see light coming from my out-of-plane dipoles. Okay? So rather than measuring across the whole Fourier space or whole backfocal plane, we can actually just make two measurements. Okay? And now, without any kind of fitting, we see the same frequency shifts that I showed you before. Okay? And now, because we're filtering in momentum space rather than fitting in momentum space, we can not only plot the spectra, but the dynamics. Okay? And so we see different spectra, and we also see different time traces of the dynamics. And this was really the proverbial nail in the coffin that really proved to us that we have two distinct exciton species. Okay? So we have two distinct exciton species. They have different orientations. And as a result, they have different spectra as well as different dynamics. Okay? So real quickly, I'll tell you how these ideas about looking at the anisotropies in these organic and layered materials relates to optoelectronic devices, since I am in an EE department. So for any optoelectronic device, whether you're talking about a light emitter or a light absorber, so an LED or a solar cell, in both cases, you want to design, for optical purposes, an architecture that enhances the light-matter coupling. So what we looked at is, again, we went back to our fruit fly of the OPV world, and we asked a simple question, which is, it's very hard actually to It's been done by very few groups in the world to be able to deposit these polymers with the vertical orientation. But we do a lot of theory in my group, so we just wanted to ask a simple question. From a purely optical perspective, which morphology absorbs solar radiation better? Right? The in-plane or out-of-plane orientation. So this we'll just call Z P3HT. Here's P3HT. Okay. Now light from the sun, so we're talking about a solar cell. So light from the sun comes with in-plane oriented E fields. So most people would think that this is clearly the better orientation. Okay. But if your molecules are sitting on a metal contact, something bad happens. Okay. The interaction of the excitons in your molecule with the metal creates an anti-parallel image dipole, and these two interfere destructively. So we get quenching of our in-plane oriented excitations for molecules sitting on a surface, on a metal surface. And in contrast, this interaction is constructive or enhanced if you have a vertically oriented dipole. Okay? So bad, good. So that was the reason we thought that this hypothetical morphology might be better. Okay? And so what we did is we looked at two different light trapping architectures, one based on metals or a plasmonic mode, and then also one based on high index dielectrics. So now it doesn't rely on this quenching effect of the metals. Okay. And since we're coming on 50 minutes, I'll just wrap up without going through the details. We can look at the surface plasmon calculations. And these are very, I believe, conservative calculations or estimates of the optical properties of this vertically oriented polymer. But what we see here is that as a function of the thickness of the film, when you include a light trapping architecture, something that takes your incident light and scatters it into all the available modes of the system, it turns out the vertically oriented polymer in red has better absorption for all thicknesses. Okay? And when we look at the dielectric mode, we see the same. And really what's coming into play here is something very fundamental. So I'll just explain that and then wrap up. So what's the fundamental difference? The parallel component of the E field is always continuous across an interface. The perpendicular component, it's the displacement field that's continuous. Okay? So because of this, let's take this dielectric gap mode, we can have an enhancement of the perpendicular field component that scales like the ratio of refractive indices squared. And that's just the field, so the absorption scales like the fourth power here. Okay? So the idea here is that, to conclude up, is that we made measurements of optical anisotropies to learn something about materials, but what that informed us was that, this is something that had largely been ignored, is that in photonic architectures for light trapping in solar cells or LEDs, it's very important to take into account these anisotropies, okay? Because the field enhancements are quite different for the different types of fields. Okay? So from a purely optical perspective, we think the ideal OPV architecture might be something like this. You have a scattering layer, which takes your incident sunlight, distributes it to all the angles, and that you design your organics so that most of the absorption corresponds to out-of-plane oriented dipoles. Okay? Similarly, we're also looking at different types of architectures which are specifically designed to enhance your in-plane light-matter interaction. Okay? But so I'll just wrap up. I won't, so to conclude this last section, the idea here was that we have these optical anisotropies that originate from distinct types of exciton species, and that we can actually exploit these anisotropies to enhance the light-matter interaction in photonic architectures for light emitters and solar cells. And so I'll just finish up with some acknowledgments. This last section of work on MOS2 and organic materials, the experiments were all done in the lab of Rashid Zia, even though I was a postdoc at Columbia, so he's at Brown. Organic samples were provided by John Comissis, MOS2 by the Shan group at Case Western. And today, you heard about Tanya's project and Prasad's and Tomer's. Stephen, unfortunately, I didn't have time to tell you about what he's doing, but he's now designed the same energy momentum spectrometer. We've built it up in my lab at Santa Barbara. We have an added capability, which is that we can control the angle of incidence for any light source. So now we can control the angle of incidence and wavelength on the excitation side. and we can measure the distribution of light as a function of wavelength and angle of excitance on the outside. And so he's been looking at very interesting properties for materials that we can deposit and then control or totally change the orientation with post-processing. Okay? But didn't have time to go into it, so I'll just finish up. I'll leave my conclusions up on the slide, and thank you for your attention.
So, questions? Yeah, I have one while they're thinking. So when you were talking about the free carrier injection by optical, so what is the ratio? Like how much carrier you can change? Like 100 times, or like when you are applying optical pulse?
So that, I guess, depends on the power of your light source. Certainly we've seen in the literature, if you're doing this in an ultra-fast way, we only need to get to about 10 to the 18 per centimeter cubed, and we've seen papers where people get up to 10 to the 20.
It depends on the intrinsic doping, or?
So we would start with either undoped or lightly doped.
Yeah.
If we're doing it optically, and then it only really depends on the intensity of the incident light beam. But actually, we're more interested now in the electrical injection method.
I think it depends on the intrinsic doping. Like if you're, at least for the silicon photonics, it depends on intrinsic doping, and you can change by only certain ratio, like maybe 100 and 200. But
yeah, so the intrinsic doping will, to some extent, control the lifetime of the excitations. Yeah. Now, in this case, once you get to high enough carrier concentrations, if the carrier concentration is much larger than the intrinsic doping, then whatever your starting level doesn't matter so much. Okay. But it would be I think it'd be pretty hard to do optically, so we're moving towards the electrical injection method.
Okay.
Yeah.
Anything else? Yeah. So if not, we can thank the speaker again.